JVA, John Vincent Atanasoff Symposium on Modern Computing. Of course, we'll talk about the root of computing, and then also we'll also take this opportunity to bring you into the modern computing landscape and what is lying ahead of us. Without no, I think I need to introduce one gentleman, Professor Lamir Gethoff, right here. He is the chair of JVA Symposium. Just make sure you know him. Thank you for all the hard work and the many other organizers for the JVA Symposium this year. I'm going to introduce our keynote speaker this morning, Dr. John Gustafson, also Professor John Gustafson, because his career spans many areas, but primarily industry and academia, and entrepreneur, venture capitalist, you name it. John has a long career in high-performance computing. John was a prodigy, actually, growing up in Iowa. He won his school science fair with a radio transmitter he had built when he was only 6 years old. His high school refused to let him take physics and chemistry because he had, just for fun, taken the SAT achievement tests in those subjects when he was in the 10th grade, and he scored a perfect 800 in all these subjects. Then he went to Caltech for his bachelor degree. Continue on after getting his master and a PhD from Iowa State. He joined a company called Floating Point Systems, where he led an effort to build the world's first massively parallel computer using common commodity parts and the distributed memory. It scaled up to 16,384 processors. And customers said he was nuts. For one thing, the national laboratories told him that no one is ever be able to go into do the supercomputing by filling the entire room with commodity processors. You need a vector machine, such as Cray. For another, the Amdahl's law says you quickly reach the point of diminishing returns with parallelism, and so no system will ever scale beyond about 8 processors. John formulated a counter-argument, but did not publish it until later years. He was able to demonstrate 1,004 speed up on an N-cube computing with 1024 processors at the Sandia National Lab. His management encouraged him to publish this counter-argument, and his 1988 paper, re-evaluating Amdahl's law, changed the course of computing and won him the inaugural Golden Bell Prize, which is the Nobel Prize in supercomputing. This argument, also known as the Gustafson law, if you Google, is on Wikipedia. He taught, his law is taught alongside with Amdahl's law, just in about every university course in parallel computing these days. John returned to Iowa State, and he found the Scalable Computing Lab at the Department of Energy's Ames Lab in Ames, Iowa. In the mid-1990s, a project formed to reconstruct the Atanasoff-Berry computer. And John joined the team, and eventually he became the leader, and he helped complete the project. For that accomplishment, he was awarded the IEEE Computer Society's highest honor, Golden Core member. Since then, he has been a director of research at Intel and a senior fellow at AMD and chief product architect as a chief product architect. But he wanted to lead another revolution, This time to redefine how computers do arithmetic. He wanted it to be completely open source. So he gave himself a sabbatical term from private employers and wrote a book, The End of Arrow, Ulam Computing. Ulam, if I pronounce correctly. The book quickly became a bestseller in this category, and attracted the attention of Singapore government. He was invited by Singapore government to become a full professor at the National University of Singapore. He spent 6 years there, and then he made a breakthrough of finding a drop-in replacement of a standard floating point arithmetic that gives the better answer with few bits. The few bits, the bits is called POSIT arithmetic. His second book is in progress, and we look forward to it. Today, John will talk about one of his favorite subjects, the Atanasoff-Berry computer, or ABC. His experience during the reconstruction of ABC provided him some unique insights on the origin of modern computing. Without further ado, let me introduce Dr. John Gustafson. And the title is 10 persistent myths about the ABC, Atanasoff-Berry computer. John.
Thank you very much, Carl. Great introduction. Let's see if my clicker works here. Okay, I wanted to point out, this is kind of interesting coming to Arizona State, that they also use red and yellow, red and gold as their colors, and they also have a fierce-looking cardinal as their mascot. So it's kind of eerie, like a Twilight Zone version of Iowa State wandering around Arizona State University. All right. I want to talk about legends versus facts. Humans love legends. They're fun. You might recognize this as the biography, maybe hagiography, of George Washington that was written by Parson Weems. It had all kinds of stories, like him throwing $1 across the Potomac and chopping down his father's tree and saying he could not tell a lie, all completely made up out of whole cloth. There's no biography there at all, but it was such fun that these things even persist in the elementary schools that they teach about George Washington. Legends can inaccurately create both heroes and villains. And usually people are not so simply categorized as black and white. There's a lot more going on. And we have to be careful not to do that when we're studying computer history. These myths definitely persist about the origins of electronic digital computing. I don't know anything that is so hotly contested. If you read the like blogs trying to sort this out, you'd swear you were looking at a political blog with the current politics, because that's how intensely religious people are about each side of the formula. So this talk will try to stick to facts, not opinions. Daniel Patrick Moynihan had a wonderful quote, one of my favorites. "You are entitled to your opinion, but you are not entitled to your own facts." So, invention versus innovation versus commercialization. And this was really brought on by a book by Walter Isaacson called The Innovators, in which he definitely made a distinction, and a good one. And he tends to glorify the innovators, not the inventors. But in any case, invention is creating a concept or a type of device that absolutely did not exist before. Innovation is making changes to things to make them better, to develop them further, to make them more complicated, larger. And commercialization means managing and optimizing innovations primarily for financial gain, like making them cheaper so that they're affordable. They're all valuable. We can honor all the people who have done each of these things, but let's not get them mixed up with each other. Let me give you some examples. Watt did not invent the steam engine. Actually, that was done by Newcomen in 1712, but he made really major improvements to it, and by 1776, he had a much more efficient design that you see there on the right. But a lot of people will tell you that James Watt invented the steam engine. Edison did not invent the incandescent light bulb. This is one that's surprising to many people. It was actually Sir Humphrey Davy in 1802 that got an incandescent light bulb working. The vacuum pumps of the era were not very good, so you couldn't get a very good vacuum. So it was hard to keep them lit for very long because they'd the filament did catch on fire. But the first filaments were platinum, so obviously not very practical. He also created the arc light, and arc lights were commercially available for 75 years, and we still use them today. If you've ever gone to an IMAX movie, you're using a light that was designed by Humphrey Davy in 1802 in order to create the light source. But what Edison did was he finally got the vacuum high enough and the filament, cheap carbon, that he could start to make a cheap light bulb that would work on as we now know it. So he made it practical. Ford was not the first to sell cars powered by internal combustion engines. That was Benz, who did it in 1885. But Ford invented a lot of very good manufacturing methods. As we now know it, his manufacturing methods made the cars much more affordable. I don't know by what factor he dropped it, but he wanted all the people who actually built the cars to be able to afford to buy them, and he got it down to that level. But let's talk about specific electronic examples of this same phenomenon. Who invented radio? Marconi did not invent radio. I mean, Maxwell was the first to describe electromagnetic waves and show that they went into the radio spectrum and they could have physical effects. But Marconi found ways of making it a commercial success. He used a lot of Tesla's patents, for example, in order to make that happen. And he finally got it to the point where you could actually transmit long distances. In 1897, I think he managed to get a signal across a fairly distinct, large body of water, like the English Channel. I can't remember which body it was, but he got an SOS across. And then from there, it advanced rapidly. Mockley and Eckert did not invent electronic digital computing. That was done by Atanasoff in 1937. But they refined it to make it larger scale in 1946, and then they went commercial in 1948. Jobs did not invent the graphical user interface. And no, it wasn't Xerox PARC either. The actual inventor of the graphical user interface was Ivan Sutherland in 1963. He started work at MIT in 1959 with Sketchpad, and he built up the entire object-oriented programming method necessary to program it, and you worked directly with a graphics display and a pen, but it was not something that was going to be a commercial product anytime soon. So what Jobs did with the Xerox PARC stuff was he drove the prices down and he got the speeds up using existing parts, and finally got to the point where he could announce the Macintosh in 1984. And from that, of course, resulted in Windows as an imitation product and so on. So we certainly owe a lot to Steve Jobs, but he did not invent the graphical user interface. All right, the Atanasoff-Berry computer. And just a little note, I share one thing with Atanasoff. The syllable on my last name is often mispronounced. It's not Atanasoff, it's Atanasoff. I have it on good authority from having worked with the family for about 40 years. That's how they say it. Anyway, it was conceived in 1937 by Iowa State College physics professor Don Atanasoff. It wasn't called Iowa State University back then. They changed their name, I think, in the 1950s. That's what he looked like about the time that he conceived the computer. You always see this picture of him as a grizzled old man, but no, this is what he looked like. He was a pretty dashing young man, actually. It was prototyped in 1939 with 25-bit arithmetic. And you see there a full adder, carry bit and everything, just as we now do it with exclusive OR and AND gates and OR gates. He said, let's use electronic binary logic with vacuum tubes driven to saturation and dynamically refreshed memory. That was one of the big breakthroughs, was figuring out how to store a lot of bits cheaply. You didn't want to store them with vacuum tubes. That would be just insanely expensive. Vacuum tubes, I think, in today's dollars, back then would cost like $300 each or something insane. Okay, then after they got the prototype, they got enough money to build a full scale, and that was a 50-bit precision machine. And they finished that in 1941 with help from student Clifford Berry, who was a mechanical and electronics genius graduate student that it was introduced to Atanasoff, and they formed one of the great technical teams of history. It had a 1,500 bit per second electronic I/O. Think of that. That was 1941. This is before we had a magnetic tape. So they used a different physical mechanism to write. They used, they actually arced holes into a dielectric material so they could then read it with an arc at a high voltage instead of creating a magnetic domain. And it had single instruction, multiple data, parallel processing which you wouldn't see again until the Eniac 4 of 1970. But he was very far ahead in thinking of how do we make the speed up? Let's do 30 things at once. It was disassembled in 1948. He had gone to Maryland to help with the war effort during World War II, and they knew he wasn't coming back. So a graduate student working in the area where the machine had been built, I think I have time to tell this anecdote, actually. It was built in a basement, but it was an open basement. The machine was about 3 feet wide. Atanasoff mistakenly thought that that would go through a door. They poured concrete walls to make offices in the basement and used standard doors, which are 33 inches wide. So there's no way to roll the thing out. They boxed it in. It was, you know, it was all built out of angle iron. There was no way you could hack the thing apart without just totally destroying it. So we asked the head of physics, G.W. Fox, what should I do with this? And he said, dismantle it. He's done with that machine. He's never coming back. And they didn't even tell Atanasoff they were doing this. But it was the person who dismantled it was a guy named Stewart, who ironically later became head of the computer science department at Iowa State University. Anyway, it was reconstructed in the 1990s. And as mentioned, I did have a part of that effort. And that's what the modern version looks like. And of course, now we can take full color pictures of it, but it's very, very close. We made it less than 33 inches wide, though, so we knew we could get it through doors. That's the one thing we changed. Okay, now the reconstruction effort lasted several years, and it really resolved many myths about the ABC, partly because in trying to figure out how to build it, there were some missing pieces that caused us to scavenge the whole human race to find anybody who had ever seen the machine working, anybody who knew how it was built, could give us any firsthand information whatsoever. We had a pretty good paper documentation. You know, we had the parts list, we had the staff, we had the schematics, we had very good documentation of the machine. But every once in a while, we'd hit something where we just didn't have coverage. And as a result, we learned a lot of stuff. Electronic switching, remember at the time, this is key. You had the Charles Babbage and others from even 1846 had conceived of programmable computers that used mechanical gears. And it was just not practical to build because there was enough play in the gears that you really couldn't drive them forward and reverse without a lot of clanking and hysteresis in the gear mechanism. Then there was Konrad Zuse, did some brilliant work and even managed to figure out a way to use motorized linkages. These are like pins intersecting slots and things that slid back and forth to record a 0 or 1. Built it on his parents' dining room table, you know, big flat thing. He called it the Z1, and it worked. It was an amazing thing, but it certainly was not going to be the start of electronic computing. He later said he went to electronic relays, which are, of course, electromechanical. You've got something that's actually moving. You're not going to get that above a couple hundred hertz ever. But it also did work. He called that the Z3. Someone said, why didn't you use vacuum tubes? And he said, that's a Schnapsidee. That's German for a schnapps idea, something you do when you're drunk. because he realized that would be really, really costly. And he was using his own money. Atanasoff in 1937 said, let's drive electronic vacuum tubes to saturation so we can do zeros and ones, which was not the way they used electronic vacuum tubes back then. They were amplifiers back then. You stayed in the linear region. So I'd like to do 10 persistent myths because I've seen books come out, both from the Eniac side and about Atanasoff and Isaacson's book about the innovators. And I think after all this time, are we still seeing these myths repeated in these books? Can we get rid of these once and for all, but just by looking at the facts? And with the help of John Atanasoff II, we sorted these into order of importance from least to most. So I'll do it David Letterman style. Persistent myth number 10. The vacuum tube was just a recent invention that Atanasoff was able to exploit. As soon as vacuum tube come out, it's obvious how to build a switching element out of it. A recent invention? Well, Lee DeForest invented the triode vacuum tube in 1906. So 31 years went by before anybody thought about using it as a switching element for a computing machine. Someone had to do that, and it was not obvious. Even after he did it, it wasn't obvious. It's used always, as I said, in the linear amplification region. You stayed away from anything where it started to go nonlinear. That would be crazy because you were trying to get these things to be like audio amplifiers. Atanasoff was the first to realize that if once you saturate it, you had the basis for fast Boolean arithmetic. You could go at extremely high speeds with vacuum tubes, switching on and off, and you'd have zeros and ones were digital. And he wanted a digital computer, what he called a proper computer. The term digital hadn't been coined yet, but he had no interest whatsoever in analog computers, which is all there was at the time. Now, the relay was invented for telegraphs in 1840. So tell me, why didn't people build digital computers in the 1840s? They had everything they needed. Why didn't Babbage use relays? There was a guy, Leonardo y Torres y Quevedo, who in 1912 said, let's build a Babbage machine, but make it binary and give it floating point. Believe it or not, they knew about floating point back then, and do it with relays. But it never happened, but he proposed it. So we know that they understood that relays could be used for computing. But it wasn't until Zuse did it a century later. So just because a technology comes out doesn't make it obvious to people how to use it in a computer at all. Persistent myth number 9. Atanasoff was a lone tinkerer in a basement with only his young sidekick, Clifford Berry, for a companion. That's a direct quote from The Innovators. I read that, I thought, what is he thinking? Is he thinking something like this? You know, Dr. Frankenstein and Igor in a darkened basement doing a secret project that nobody knows about? That is absolutely as far from the truth as it could be. I mean, at Nassau, at Iowa State, first of all, he had a team of 6 paid grad students. Like any other professor, he was always advising grad students. They meet on Monday morning at 9 o'clock. They discuss what they were going to do for the week, and they start working on the machine. It was a well-lighted university work area. The fact that it was in a basement doesn't mean it was different from any other work area on campus in the physics building. And he was well connected to other researchers, including John von Neumann. He would go to the American Association for the Advancement of Science, AAAS back then, was the big conference, every December. So he was completely connected to the community. They knew about him, he knew about them, and that's where he met John Mockley, who said, oh, I want to see this machine you've got, after he told him a little bit about it. I believe that Walter Isaacson may view Iowa as flyover country. This is very common among New Yorkers. And they know the 9th Avenue, 10th Avenue, there's the Hudson River, and then there's a bunch of stuff. There's like the rest of the country and China, Japan, Russia. But they think so much, everything is New York. And this Saul Steinberg cartoon is a real classic. But I sense that in him saying that, well, if it happened in Iowa, then nobody knew about it. And it was completely obscure, so it was completely lost. Not true. Okay, persistent myth number 8. The ABC inventors never did anything more in the area of computer development, and certainly did not try to commercialize the invention. From the Computer History Museum in Mountain View, California, you can see this little device. From Consolidated Electrodynamics Corporation, CEC, in Pasadena, they introduced the first commercially available electronic computer, which is the CEC 30-201. And it was particularly good for solving systems of linear equations. Kind of interesting. It was the first commercial computer. It was bought by, CEC was bought by Burroughs, and that switched them from mechanical to electronic computing. Burroughs actually introduced the B205, which had been spearheaded by one of their engineers, and that made them competitive with IBM and Sperry. So you had 3 mainframe makers, and eventually, Burroughs rose to become the #2 computer company. You could never beat IBM back then, but finally you could be #2 to IBM. That was the goal, was to be the 2nd biggest computer company. The lead engineer on the CEC 3201 was Clifford Berry. He was also the one, he became lead engineer, and he spearheaded the 205. That became the basis for all of Burroughs' mainframes. So really, just about every modern digital computer can be traced back to the ABC, either through an official route or through the conveyance of information, not necessarily by legitimate means. Persistent myth number 7. The ABC was never used for production computing. Actually, it was. It was used for real workloads. It was used a lot. If you do statistics, even if it's a simple linear fit, you have to solve 2 equations and 2 unknowns. And that can be tedious back in 1930s. especially if you need it very precise. The kinds of equations you get when you're doing curve fitting tend to be not very well posed. You need high accuracy. You need like 15 decimals to make sure you get it right. And when Professor Snedeker heard about this, he sent a steady stream of AX equals B linear algebra problems to Atanasoff teams. And it would be sent, he'd send the results back, and then the department secretary, whose name was Clara Smith, it's a lot easier to check that A times X equals B than it is to solve AX equals B. It's like doing a multiply to check a divide, a lot simpler. So it was her job, and we spoke to her when we were on the reconstruction team. She was still alive and living in Iowa, not hard to find. She had all kinds of stories about how it was used for production computing. Also, we spoke to original team member Robert Mather. He's one of those 6 grad students living in Oakland. He is a physicist, and he informed us where the output of the computer was. We could not find anywhere. Where's the output? We knew how the data got in, but we didn't notice the little odometer that was right next to the card reader that rotated to produce a numerical answer. Finally, we solved that problem. And he said that they would actually, before they did production runs, they'd check the computer by giving it a 5x5 matrix to solve. And that was just like the right size problem to be big enough to test it and see if it's all working, but not so big that it would start to get into reliability problems or just take way too long to solve. So he was very helpful. If you see the really sharp black and white photographs of the ABC in historical record, he's the one who took those pictures. He was very proud of his wiring. He did the wiring. Persistent myth number 6. The ABC was not fully electronic like the Eniac. It had mechanical components. And this is another quote from the innovators, which gets repeated again and again and again. I think they see the motor and they go, mechanical. It's got a motor, it's got to be mechanical. Well, guess what? Hard drives have motors too. And we still use those. The switching logic was 100% electronic. There was no mechanical anything. There were no relays. There was nothing to flip when it came to doing the calculation part. Like modern disk drives, it had memory to rotating drums. In fact, that was the most patentable, one of the most patentable ideas in the ABC was spin the memory and keep it alive. It was clocked by wall power, 60 hertz. Hey, it's easy, right? You plug it in, there's a clock. So he had an electronic clock. He didn't push hard for the clock. He probably could have done super harmonics of the wall clock or something like that. But it was already so fast and so limited just by the I/O of the card reader that they didn't bother going past 60 hertz for the actual calculation. Like all early computers that had punch card input, that's mechanical. It was read mechanically, just like the Eniac had punch card input. And it used electronic I/O. Now that was novel. He was so adamant, he wanted the machine to be all electronic. He even wanted the scratch results to be all electronic and not to like having to punch holes in things. And he got that almost working. I'm one of the few people who has both used the Atanasoff-Berry computer and also twisted dials on the Eniac, because I snuck into the Smithsonian and reached behind the plexiglass. Just wanted to get a feel for what it was like to adjust those dials. But it had, for every time you wanted a different constant, you had to set 10 dials to numbers 0 through 9 in order to enter it. The Eniac was not a programmable machine. It was a reconfigurable machine. There was no way you could give it a different program. More on that in a minute. Persistent myth number 5. Atanasoff, this is very legend-like. He jotted down the 4 principles of electronic computing on a napkin after consuming drinks at a roadhouse he had spotted during an aimless long drive. Now, Atanasoff is partly to blame for this one because he was asked to tell the story so many times, over and over again, that it started to kind of wander away. We were later able to trace exactly what happened that night that he said, I'm frustrated, I can't solve these last few problems. I'll go for a drive. He did that in those days. He would go for a drive when he wanted to solve problems. But this was, well, look at this and say, okay, aimless long drive drinks. It was a place I had been before, he said. Drinks? Yes. Long drive? Yes. Okay, start from Ames. What is the closest place you can get alcohol? Post-prohibition. He made a beeline at between 90 and 100 miles an hour. 200 miles later, he was in Illinois, which had actually had legal bars by that point in a place in Rock Island. But Iowa was a dry state. The guy just wanted a drink, okay? And he did think about it on the way, but he didn't really make the progress until he sat down and had a couple of bourbon waters. He didn't really need a napkin to record his ideas. He kept ideas in his head. He might have jotted things down on the napkin just to help him, you know, doodle. But 4 principles, more like 10. All kinds of things had to come together. That like it was just the last few pieces coming together that happened when he finally had a couple of bourbon waters, and everything fell into place. It was not a eureka moment. He had been writing about electronic digital computing for years and years before he actually said, I think I know how to build it now. And his wife was very happy when he came back in the wee hours of the night and said, I think I've solved my problem. I know how to go forward now. So she was very tolerant of him going all the way to Illinois for a drink. But when asked what was the place you visited, he didn't want to name it. It was a place he'd been before. It was Rock Island was kind of a happening place. It was the closest thing to Las Vegas in the middle of December in 1937 you could possibly find from Iowa. So I think just getting out of the Iowa winter and someplace fun probably also helped him a lot. Persistent myth number 4. The ABC was never finished, or the ABC was never fully operational. Just about every interview with J. Presper Eckert, it has him saying something like this. It was just a piece of junk, it never did anything, and even if he'd finished it, it never would have done anything. He really wanted to denigrate it. The ABC worked almost perfectly. The almost is in the I/O unit, because that method of punching holes with a thyrotron tube got a wrong answer about every 10,000 or 100,000 bits. And that seems like a lot, but no, you've got to go through millions of bits if you're doing a big system of linear equations. And that practically limited how large the problems could do. But we found a whole bunch of problems could be done without any scratch storage at all, which means the rest of the machine, that's what determined the reliability. And that was rock solid, is as rock solid as any modern appliance. We did not improve the ABC when we rebuilt it. There were temptations of using more modern computers, more reliable. We did it exactly the way he did it, okay? I remember one tiny improvement. They said, let's use modern coax instead of the cloth-covered wires that they used in one part of the connection. And sure enough, when we soldered them, the solder melted the insulation and made a mess. So we realized they were right to use cloth-covered wires. So stop trying to improve it. Just do it exactly by the book. Berry kept on working from 1941 to 1942, and World War II just decimated the group. Atanasoff went to the Washington area to join the Naval Ordnance Lab and help with the war effort. Clifford Berry went to this company in Pasadena, where they are also doing war-related research. And they left the machine kind of in the hands of a professor who said he'd keep an eye on it. And that's why we still have one of the drums of the machine. And I think we still have one of the add-subtract units as well of the original machine. But it really dispersed the group. Interestingly, in 1942, I said there were 6 graduate students and a secretary. Secretary's name was Jean. She married Clifford Berry. So they went to Pasadena together. And Jean Berry was also very helpful to talk to about what was going on in that era. The ABC certainly worked well enough for production runs. When you say that a machine breaks down now and then, I've worked on supercomputing 30 years, and supercomputers sometimes break as much as 20 times a week, like ASCII Blue Mountain, or the latest, actually, the one at Oak Ridge is having more troubles than they like to admit. But that's what happens when you push things hard to the very limits, you get into reliability problems. Seymour Cray said if your machine doesn't fail at least every 2 weeks, you're not trying hard enough. You need to get very close to what you can tolerate, or else you're not doing supercomputing. So I think they had it just about right. You never say that a machine's not operational just because it occasionally has a failure. Persistent myth number 3. Unlike the Eniac, the ABC was special purpose and could not be programmed. I may be the only person who has found a counter argument to this, and it was completely new to me because I believe this too. I was always told it was special purpose, it was for solving system equations. And I look back on some of the things that Atanasoff had written, and he said, if you can solve systems of linear equations, you can do all kinds of things. He knew, but didn't explain it very well. So let me explain what he meant by that. First of all, the Eniac was reconfigurable. It was not programmable. It took about, they had a team of 6, mostly women, I think, who would unplug and recable things and set all the new dials, plus the time to figure out how the program could work with the limited amount of hardware they had. But it really took something on the order of 20 man days to get a different program loaded onto the Eniac, and they almost never changed it. But the ABC could actually evaluate basic blocks of plus, minus, times, divide, and polynomials and Taylor series. That was a revelation. So time for a little math. Warning, math ahead, okay? Any expression using plus, minus, times, divide can be written in the form of Lx equals y, where L is a lower triangular linear matrix. And it's a partial ordering. You say, this temporary value is this. This depends upon the previous temporary values. This is calculated from these temporary values. These is calculated, it's always from previous values that you calculate something. That is what a lower triangular matrix describes. For example, F equals A plus B times C minus D divided by E. So I got all four things in there. Does that look like a system of linear equations to you? Doesn't to me. It would never occur to me that you could calculate that with the Atanasoff-Berry computer. Well, if you set x1 equal to A and then say, well, x2 is A plus B, that's x1 plus B. Then you multiply that by C and so on. When you get to the divide part, notice that the E shows up on the left-hand side of the equation instead of the right-hand side, but it's still a system of linear equations. Just things times the x sub i's, added up. So the matrix for that looks like this. And there are compilers that can automatically generate that matrix from the formula, for any formula like that. The so-called XSC compilers from Ulrich Kulisch, which are used for doing extremely high precision calculations, because you can solve this matrix and then you can correct the error and you can get things to within, you can get the rounding error way down. So it's still useful to this day to think about lower triangular matrices as ways of doing basic blocks of code. When you solve it, you just push one button on the ABC, say solve, it cranks and cranks and cranks, and you say read out the value of x6. x6 is F. That's just the way things work when you do lower triangular systems. You've evaluated that function. And you can also reliably evaluate polynomials up to 28th order with 15 decimal precision. 28th order means 29 coefficients. The way you do that in a matrix is very systematic. You put the coefficients over on the right-hand side, and you put a diagonal of 1s, and the negative x values just in the subdiagonal. You solve that, and the very bottom right-hand corner will be the polynomial value. It did not require the scratch I/O unit, so you could do 28 and not have to worry about that mass I/O thing. And then I realized what a powerful machine this was. They said, oh, they had log tables, they had cosine tables. You didn't need this to evaluate Taylor series. I said, how many of those tables went to 15 decimal places for 15 decimal input? None of them. You had to interpolate. So actually, if you really did need high precision scientific elementary math functions, the ABC could evaluate it better than anything else in existence at the time. Persistent myth number 2. I'm going to be way ahead of time. These are going fast. I'll catch us up on time. Atanasoff neglected to patent the idea, leaving others to do so. He didn't neglect anything. He completed the patent application from day one. He said, this is a hot one. This is going to be worth something. And he immediately went to the Iowa State Research Foundation and started negotiating. And initially, Iowa State said, we want 90% of the profits from this, and you get 10%. He said, how about 50-50? And he had already promised 10% to Clifford Berry, because he really appreciated what Cliff Berry had done to help invent this machine. And finally, they got it to be, okay, 40% for Atanasoff, 10% for Cliff Berry, and 50% for Iowa State. And with a guy named Trexler in Chicago, they filed up, I mean, they didn't file it. They completely filled out the patent application, finished it, all the diagrams, and Atanasoff would routinely ask, how's the patent coming? How's the patent coming? How is the patent coming? And he sometimes would get meaningful answers, but sometimes he'd get the runaround. They wouldn't really tell him what was going on. Now, the ISC president, I believe it was Friley is his name, decided without telling JPA, it's not worth the money. That's really expensive to patent something. World War II had started, and it just didn't seem like the highest priority. So he did a pocket veto of that patent and never told Atanasoff that he hadn't bothered to file the patent. So I think after all these years, we now have a very, very clear idea of what happened to the patent that was so carefully prepared and that they wanted to file. But it was every couple of weeks, Atanasoff would say, has the patent been filed yet? Because he was very concerned about losing his invention. Okay, it was never sent to the US Patent Office. He knew the idea was valuable, and when Mockley came to visit, he told Mockley, now, I think I filed for the patent, I've got the papers ready, but don't take anything away from here, please. I'll trust you. As a fellow academic and a colleague, we know that, you know, we're cool with this. Don't pirate any of my ideas. And he trusted him not to. Mockley pirated the idea very clearly. The audit trail is completely clear. So persistent myth number one, after this came to trial. Maybe I'm leaving out too much here, but it was quite a story. There's a book by Mollenhoff called Atanasoff, Forgotten Father of the Computer. I've got a copy over here. It is the best book ever written about the Eniac versus ABC controversy by a Pulitzer Prize winning reporter, investigative reporter. And it goes through every little detail that you would need, but no more than you need. So it's a quick read. It's actually a page turner. And the drama is really incredible. They should make this into a movie. They made an entire movie about the invention of the intermittent windshield wiper. But not the computer. There are suicides suspected to be murders, and there are swimming accidents also suspected to be murders. There's a lot to be had here. You can't make this stuff up. In the whole history of this controversy, it's a big one. But we do know that Mockley went to Ames at the invitation of Atanasoff, and in June 1941 spent 5 nights and 4 days expecting to be fed and taken care of by Mrs. Atanasoff, and also for her to babysit little Jimmy, his 6-year-old, along with the 3 Atanasoff children, which she kind of resented. She didn't like Mockley very much. And he did nothing but tear into Atanasoff, asking him question after question after question. But there was no indication ever found that Mockley had thought of the idea of digital electronic computing. Analog, yes. He wanted to build an imitation of the Vannevar-Bush differential engine that they had at MIT. But he didn't even have the concept of digital computing. So they had this court case, started in 1967, and it lasted 6 years. It was finally resolved in 1973, I think in October, and the news hit of the judge's decision the same day that they announced the Saturday Night Massacre of the Watergate scandal. And so you could not find this except, you know, on page 27 in the newspaper, the fact that they now announced that the patent had been broken for Sperry owning the patent on computing. They generated 32,000 exhibits, 20,000 page transcript. This is one of the biggest federal court cases ever. It cost, I want to say, $13 million to try back then. And I think it would be about $40 million to do it now. So this would be like investigating the Mueller investigation. It's on that scale. Huge, just huge. And the only way you can do something that huge is if you've got giant computer companies on each side, like Honeywell versus Sperry, maybe with a little bit of IBM thrown in there too. So once you've got that kind of money, and the stakes are so high, because being able to control who gets into the computer business and who doesn't, that was how they maintained a kind of an oligopoly back then. They didn't let little players, you know, like Steve Jobs, get in there with his PCs. No, they hit him so hard with royalty demands that he'd never be able to get off the ground. So the case after they decided was never appealed. And how could it be? They'd exhausted every single thing they could find to show that there was innovation on the part of Mockley and effort before they learned about electronic digital computing. They started the project of the Eniac in mid-1942 after they'd thoroughly exhausted all the information they could suck out of Atanasoff in 1941. Until then, there was absolutely nothing that looked anything like the Eniac. So Mockley claimed on the stand repeatedly that he knew all about digital computing. He'd been thinking about it for years, and it was before he met JVA, who he barely met, only spent like a day and a half with, and the machine was under recovery. He never actually saw it operate. He did 3 depositions in which he kept having to change his story as they brought forth more and more evidence that he was a liar. And the judge was very kind in not accusing him of being a liar when he finally did his final judgment. But it was very clear he had perjured himself repeatedly on the stand and not stated what he had learned and not all the things he had seen actually working. But the thing that really gets me is when he was asked to prove he knew what digital computing was, he brought out a toy that he'd once built on the top of a Quaker Oats box, had a little neon tube. And he hooked it to a battery and maybe a couple other parts such that it flashed on and off. He said, there, digital computing. How so? He said, well, it counts from 0 to 1. And then it overflows and goes back to 0. And now they say the judge wasn't technical enough to really make a good judgment. I think, you don't have to have a technical degree to see that you're being flim-flammed with stuff like this. There was no, as I say, no indication that digital electronic computing ever occurred to Mockley and Eckert. So, tech expertise is not needed for core questions. Did Mockley visit John Vincent Atanasoff? Yes, for 4 days. Did he see the ABC in operation? Yes, for 4 of those days. They crawled under the machine. He helped walk it around to a place where they could plug it in and so on, and he was all over it. Did Mockley write letters to JVA asking for permission to use his concepts? And they even said, could we build an ABC calculator here at the University of Pennsylvania? And Atanasoff kept all of his letters, and he eventually found all of them and was able to produce them for the court case. The lawyers for Mockley said, please remember as little as possible. Did Mockley read the 35 detailed transcript of the ABC? Yes, he did. And this part of the story is one where I've made up my mind, but I won't state it as a fact, just a really strong suspicion. He was shown this 35-page document. It was the way they made documents back then is they had carbon paper, and they type it, and that would give them triplicate. They gave 2 copies to the Iowa State Research Group, and that would give them one that they could use for filing and one to keep for their own records. And Mockley said, can I have a copy of this? And Nassau said, no, I haven't finished the patent yet, and that's over the line, okay? You cannot take that with you. So could I take some notes from it then? And reluctantly, Atanasoff said yes, and he asked Mrs. Atanasoff for a ream of paper. And he took it up to his room for the night, and they could see that the light was on underneath in his bedroom all night long. It looks like he was hand copying the entire 35 pages, but we don't know that, okay? So this is a non-factual suspicion. He really did steal, word for word, what was in that 35-page description. He had a lot of trouble understanding some of the things that were in it. He especially didn't understand the binary part. He really wanted a decimal computer. This idea of something that's not base 10, it just kind of blew his mind. He couldn't get his head around that. And there was a lot of correspondence between them over the next months of where he would ask questions of Atanasoff about why he did that and how. He was the student. But as I said, a ruling was marked by news about the Watergate scandal, but here's just part of the final ruling. Eckert and Mockley did not themselves first invent the automatic electronic digital computer, but instead derived that subject matter from one Dr. John Vincent Atanasoff. You can't be more clear. I know from John Atanasoff II that the judge privately told him, those guys are crooks. He didn't put that into the ruling, but he realized that they had pirated. It was one of the biggest cases of intellectual piracy, probably in human history, to steal that kind of an idea. And then the Mockley and Eckert people did not even share credit with their own team. They had a team of 20 people on the act, excluded not part of their patents or anything like that. They said, we did it all ourselves, all by ourselves, the two of us. So you know there's something wrong here. Because they were so interested in commercialization, they had to fence it in. They had to totally own it. That's the only way they could be the commercial computer company of the 1950s and going forward. So I believe that Mockley and Eckert deserve credit as innovators, definitely, and commercializers, but not inventors. So, getting towards the conclusion, what this did was it unpatented the computer. As soon as you broke that patent, it's not like Atanasoff could then patent. It was way too late by then, which means nobody owned the patent on computing, which is what von Neumann wanted in the first place. Von Neumann wrote this paper about principles of computing in the 40s, and Mockley and Eckert said, what are you doing? You're giving it all away. And that was kind of the idea. He thought it was too big of an idea, von Neumann, for any one person or two people to own and have fenced in. He wanted the world to know what computing could be. So he did the same thing Turing did. He wrote a paper about it that would, put it out there. But as soon as you unpatented the computer, this is 1967, a lot of companies started working a lot more enthusiastically on entering the market. Apple introduced its first personal computer 3 years after that ruling, the Apple I. And that was quickly followed by the Tandy, the TRS-80 Radio Shack, and the Commodore PET. All came out in 1977. DEC introduced its very successful VAX 11780, architected by Gordon Bell. And they sold a couple 100,000 of those, which is a lot for a mini computer. Suddenly you didn't have to rely on big mainframes where you submitted a card deck to it and waited 3 hours for your answer to come back on fanfold paper. You got something a lot more interactive and a lot more modern with a VAX. And universities adopted those, as I say, by the thousands. Also, Seymour Cray introduced the revolutionary Cray 1, which broke so many bounds in so many ways. All that happened in 1977. Actually, the Cray was in December of 1976, but let's call it 77. So you've got a supercomputer, a mini computer, and personal computers all in the same year. The industry has completely changed as a result of the unpatenting of the computer. So the industry exploded with success. It wasn't long before computing was 10% of the US economy. I don't know what it's at now, but I think it's a lot more than 10%. When you look at the trillion-dollar companies that are out there, and is Tesla a computing company? I guess it mostly is. You could think of it that way. Certainly Apple, Facebook, all these big companies that are monsters with trillion-dollar valuations are all based on computing. So, Atanasoff died in 1995, but he lived long enough to see his achievements recognized. He was near the White House, and they suggested that he come and watch this ceremony that President Bush was conducting. He didn't know that he was about to be given an award, the National Medal of Technology. He was called up to the podium to receive it from President Bush for having created perhaps the greatest invention of the 20th century.
Thank you, John. Actually, I listened to the earlier version of this talk back in 2006 in Sofia.
Oh, it's very different now.
Yeah. But every time I listen to you, I learn a lot. It's always refreshing.
Thank you.
Thank you for that. We apologize for the delay initially, but I think we still have time for 1 or 2 questions from the audience.
We start the panel at 10:50, is that right?
Yeah,
so
I think we have to push down a little bit. But any question from the audience? Otherwise, the next session is also on the same subject with Professor Gethoff. If you have questions, we can delay to this session to ask. How about that? Because we are late and behind for our coffee break. Or we can take one question. Yes.
Yes, so this is a wonderful talk.
Please get a
could you use the microphone?
Okay. Yeah, thank you for your wonderful talk. I had a quick question. I think you commented on it when you discussed the degree polynomial that can be solved. What's the largest system that the ABC could operate on?
Well, it was 29 equations and 29 unknowns.
Yeah.
So that means you need 30 columns because you have to have the right-hand side.
Yeah.
So it was doing vector times scalar minus vector was the primary operation to eliminate one row from another row, and it kept on going until this coefficient was 0, then it progressed to the next one and the next one and so on until you would solve the entire system. But 29 equations and 29 unknowns.
That's a computer.
Yeah, it took about 8 hours to do.
Thank you.
If it was in flops, it would be 0.06 ops. Flops, not megaflops, flops. Back here.
Okay, we have one question back there.
Fascinating talk. Please, can you show or give the title of the book you mentioned again?
Atanasoff, Forgotten Father of the Computer.
Okay.
It's usually
Thank
sold
you.
with a kind of a blue-green slipcover on it. Great book by a guy who really knows how to write because he's a journalist. As I
On
say,
my
a Pulitzer
bookshelf, I
Prize
have
winner.
another 7 books, all on ABC, JVA legacy. So, all right. So I
I thought
think
there was
I
one
will-
more hand somewhere.
Any one more question?
Maybe that's it. We can save it for the panel.
We'll save for panel. All right. So thank you again.